Hi, it's Chris Sandwich here. I'm excited to talk to you today about SciFi's RISC-V vector extensions and how we're using these to scale intelligence to the edge. So today I'll be talking about the scalability challenges of building these AI edge solutions. I'll talk about SciFi's solution, how we view RISC-V with vectors as being a great approach to handling problems in implementing AI at the edge in SoCs. In particular, how it helps with software development. We'll talk about how RISC-V vectors are more efficient than conventional PAC SIMD in regular application processes. I'll also preview the auto-vectorizing compiler work we're doing at SciFi. I'll also dive then into the core IP that we've been developing around vectors. So the VIU7, the application core, and describe its microarchitecture, and also announce the VIS7, the embedded version of the 7 Series vector intelligence core. I'll also give a few initial benchmarks of the core just to see how well we're doing in terms of performance. So when people implement AI at the edge in SoCs, there's often a big challenge in terms of what algorithms will users want to run, how will they want to run them, what size of problems are they going to run. And so, and to meet these needs, people have developed a diversity of accelerators that have very different instruction sets, proprietary APIs, libraries that match those, proprietary accelerator APIs, and some algorithm classes. But as you go from building the design to taping out the SoC, this is a very fast-moving field. So AI algorithms are changing all the time, many new improvements coming along. And the worry is that when you build this SoC, that the part you've put on there, the accelerators, don't really match the algorithms at the time of deployment, or you may find different customers for that SoC have very different algorithms they'd like to run on that SoC. And as well as being a poor match, it may have a less than ideal programming environment for these accelerators, typically not as well supported as a conventional processor. And power optimization can also be very difficult to implement, as well as other features you expect on processors on an SoC. So our solution is to base our edge AI solution on the industry standard ISA, RISC-V with vectors. And this is great for the customers, as using a standard RISC-V vectors prevents vendor lock-in, and also enables us to build a very rich shared software ecosystem for AI. Scalable performance with the RISC-V vectors allows us to meet these AI processing requirements from very low power, very area efficient cores, all the way up to the highest performance compute cores. A SciFi solution as well is not just a single core. We can integrate multiple cores, and those cores can be application class cores that support Linux, or they can be real-time cores, or even including embedded accelerators. And these can scale up to multi-TOPS performance. We implement an efficient memory hierarchy underneath these multi-core complexes. But having this single ISA across the cores for supporting these vectors makes a much simpler and more efficient programming model, and also allows the cores and the code to be tuned for each algorithm and to support a wide range of algorithms at high performance. Because these are based on our application cores, we have a comprehensive security support, as well as on the embedded cores, implemented by SciFi WorldGuard, our security solution. We also have advanced trace and debug available on all of these cores and on the whole SoCs. So RISC-V with vectors enables efficient AI SoCs, and this gives a sketch of how we view people using these. So you build the main core complex using a combination of our scalable vector cores connected coherently through a multi-level cache hierarchy, and you can have multiple cores in each of these clusters. And by using a multi-core complex this way, you can really tune code to really efficiently use that memory hierarchy. If you want the very highest performance, you may want to still attach a custom deep learning accelerator. These can be coupled into the core complex and, for example, share the L3 cache to transfer data between the accelerators and the application cores. This leads to a very simplified model of an SoC, quite conventional in some ways. It's very area efficient and can result in much lower power, as you don't have accelerators that aren't being used lying around. It provides a binary compatible platform all the way from tiny embedded cores to supercomputer class multi-core clusters. So you can really scale the performance you need from by using a small single core or going up to multiple large cores. Now, the big reason for moving to RISC-V vectors, it really helps with software. And the key to getting good application performance on whole applications, not just single kernels, is a rich software development environment. So RISC-V vectors enables this. There's a single ISA that allows us to build libraries that can be reused across different sizes and classes of cores. The RISC-V vector architecture was designed to be vector length agnostic, which allows us to have library code be reused across different generations of cores and across different sizes of cores within the same generation. So the same binary can actually run on tiny low power cores that you might use in a wearable or on a high performance supercomputer class core. We've already announced the Linux capable VIU7 cores, which have up to 48-bit virtual memory support for large data sets and support Linux. Just boot Linux on these cores and then run vector code on those cores. And we'll be leveraging the open source community who've been doing a lot of application development, including projects such as bringing OpenBLAS and other things like TensorFlow Lite over to the RISC-V standard. And we really view RISC-V vectors 1.0 becoming the industry standard for a lot of this work. Now, one thing we like about RISC-V vectors, we view it's much more efficient than conventional packed SIMD ISAs you see in a lot of other architectures. And this slide is showing some, by now, quite old work on comparing RISC-V style vectors against traditional packed SIMD and other instruction sets. And what you really see here is, this is just using a simple kernel as an example. RISC-V vectors give you much smaller code size, so you need many fewer instructions to describe your loop. And so the code size is reduced, but also when you're executing the code, you need many fewer instructions to dynamically execute the code, which results in a lot of power savings too. You can be a lot more efficient as you're fetching and decoding and issuing many fewer instructions, even with the packed SIMD architectures, to get the same or greater performance. Now, harnessing that performance really needs effective software development environments. At SciFi, we're very fortunate to have the inventor and lead developer of LLVM working at SciFi. We've been busy building out an auto-vectorizing compiler. And this is just a preview of what we've been able to do. This is still early stages, so there's some improvements we could make to this generated assembly code, but it turns out this loop is actually memory bound, and so this is actually pretty close to the best you could do with hand-tuned code in terms of absolute performance. We are introducing the VIU7 today, and together with our multi-core capability, this gives us a broad spectrum of vector intelligence 7 series core family to cover a lot of application needs. So VIU7 is the embedded core, and this is suitable for a lot of applications traditionally done DSP, voice audio, as well as smart voice and AI. The application class core VIU7, a lot of applications, industrial automation, smart cameras. And then you can combine these cores, mix and match to build larger multi-core clusters for higher performance levels, such as you may find in autonomous vehicles or ADAS systems. So we have a very broad spectrum of performance demands met by using different cores and then configure them into larger clusters. And you can start eval on all of these today. So let's dive in and take a look at the VIU7 series. This is our application class core for the Vector Intelligence 7 series. So the base core is derived from our SciFi VIU7, a Linux core. And this supports the full RV64 GCV instruction set with up to SV 48-bit virtual memory support. So the base pipeline is an 8-stage dual issue in order pipeline, and the vector unit has been added as a decoupled engine to the side of that dual issue scalar pipeline. The VIU7 supports machine supervisor user privilege modes, and it also allows for single and coherent multi-core options. We support the full standard vector instruction set v1.0, all the features that will be in the standard. Floating point, fixed point, integer data types. We can compute up to 512 bits per cycle and 8-bit to 64-bit data types. Some other key things about the VIU7, we can combine this in a cluster with other embedded cores, including just regular S7 cores, embedded cores, as well as VIS7 cores. And so those embedded cores can act as system monitors, I/O processors that run in parallel and are using the same coherent memory system as the application cores. There's a private L2 cache on each of the VIU7 cores, and optionally you can have a shared L3 cache in the cluster that's kept coherent between all the cores, mix and match cores, Unix cores, or embedded cores in that same cluster. We support the PMP features for security, as well as SciFi's WorldGuard security features, as well as SciFi's advanced trace and debug on these core complexes. So diving into the microarchitecture of the core, so just looking at one core now, there's a dual issue scalar unit. This runs concurrently with the vector unit, runs ahead. In the VIU7-256 variant, we have an ALU pipe that has 256 bits of memory width and also 256-bit width of inputs to the ALU operations. The vector length is 512, so that's 512 bits in each vector register. For the simple vector operations, it takes 2 cycles then to complete a single 512-bit operation when L-mul is set to 1. We have separate memory and ALU pipelines that work concurrently, and we can chain between these when vector operations are running. So the vector ALU, it's a 256-bit input ALU, but it can actually produce 512 bits of result per cycle when you're performing widening operations, which are quite common in lots of AI applications. So you can do 4 64-bit, 8 32-bit, 16 16-bit, or 32 8-bit ops per cycle. And again, if those are widening operations, they'll expand out to 512 bits of result per cycle. The vector load stores are highly decoupled. And the way this works is the vector loads and stores check in the scalar L1 data cache, but actually stream out to the L2 cache and use that directly as primary memory. So in fact, there's no load to use penalty on vector code that's running on loads that are hitting in the L2 cache. So this really gives a big advantage, as you can keep a much larger working set in the L2 for the vector workload, but have the tight L1 scalar cache close to the scalar processor, keeping low latency for scalar execution. So we're introducing today the VIU7. This is our embedded version of the VIU7. This is a 64-bit embedded core. It's designed for embedded applications. It has lower power and area than the VIU7. The base core is derived from the S7 series. It supports the full GC-V instruction set, but now with only machine and user modes. It doesn't support the privilege mode, supervisor privilege mode. Again, this can be combined in a coherent cluster with other cores, including our regular embedded cores without vectors. It supports the full set of RISC-V vector extensions, and PMPs, the security features, and the trace and bug debug features we had before. So really, this is a stripped-down embedded version of the VIU7. So we have eval systems available now for both of these, the U7 and the S7, based on a Xilinx FPGA board. And you can run single or multi-core on here with debug available. And the integrated development environment knows about this now, as well as the compiler, intrinsics, and QEMU targets available, as well as a System C model to include in your modeling work. Just to show you a slide here, this is just showing SciFi Insight, Advanced Trace and Debug, running with the vector core. And you can see here that vector instructions are supported fully as a first-class citizen in the debug system. You can click on those and expand out and see what's happening inside the execution trace of the vector instructions. So just some preliminary benchmark numbers. So we're comparing here against the ARM Cortex A53, which is another application core. Comparing the VIU7 against there. And this is a simple 5x5 Sobel filter optimized for neon extension on A53. And we're seeing on the VIU7 getting over a 6x speed up over that ARM Cortex A53 on this particular kernel. Another example is on DSP workloads. This is a 1D convolution here using 16-bit fixed point. And what we're showing here is on the 256-bit VIU7, as we increase the filter size, we're approaching around 80% utilization of that ALU on this 1D convolution. So getting good performance there on this kernel. Another example kernel is matrix multiply, very important in many applications. So here we're showing operation on square matrices with random data. And we're storing these matrices in row major order. And we're just showing here, as you work on different precisions, how the utilization is affected. So half precision matrices of a certain size have fewer bits of data in them. And so they keep the vector unit less busy, whereas larger, wider operands like double precision, it takes fewer elements to keep the vector width busy. But all of these, basically, once you get to relatively small matrices and tens of elements, you're hitting 90% and above, and efficiency in terms of utilization. And all of them approach full 97% utilization and above on larger matrices. Those were kernels, but if we look at full application performance, one example is MobileNet. And here we just show the ability to run all these different shapes and sizes of network on our core. And here we're comparing a scale result with an FPGA implementation of the VIU7 on a that's been scaled up to 1.8 gigahertz performance against an ARM A53. One thing is the FPGA, we've tried to model the memory system, but your actual performance will depend on the memory system you build into an ASIC. But on this example, we're seeing about roughly over a 4x speed up over the Cortex A53 on this full application workload. And this slide here is just showing you the screen output of that application running on the FPGA. Just showing you booting up, running the MobileNet directly at the command line on that system, running on top of Linux. And actually, it's funny that on this FPGA, it turns out the clock rate is such that we actually beat the A53 on this benchmark on the FPGA. Just to summarize, RISC-V vectors enable a wide range of edge AI applications. We have a scalable architecture of SciFi vector intelligence, and it gives you this compatibility from small embedded cores all the way up to high-performance multi-core, multi-cluster solutions. SciFi intelligence, VIU7 is the application core, VIS7 is the embedded core. These are RISC-V version 1.0 compliant core IP. We can mix and match these for Linux and real-time apps, fully supported with our security solutions, including SciFi WorldGuard, and also fully supported for trace and debug. So please go visit sci-fi.com to get started with SciFi vector intelligence technology.